Hi everybody, this is Furkan. We had a lecture on Hadoop previously, so now in this lecture we'll cover Spark and its basic and try to come up with understand the differences between Hadoop and Spark and how things evolved from Hadoop to Spark. So before going into Spark detail, let's get a quick review of MapReduce and Hadoop, what we did last time. So MapReduce was originally developed by Google, um, and then Yahoo developed Hadoop on the MapReduce principle. And the basic idea of MapReduce was to write easy application that can be distributed across all of the clusters. So the main goals in this particular to designing Hadoop and MapReduce was parallel and distributed processing and fault tolerance and on a number of commodity machines. So what did Hadoop and MapReduce provided us? It provided us with you just wrote some application, some basic knowledge, and submit that to Hadoop and MapReduce framework, and that framework takes care of all the scheduling, monitoring, and executing all of the tasks. And if something fails, it's because that can happen a lot, although not in our general assignments, in small assignments that we did in our course, but in for general real time, practical real time, large clusters and applications, a lot of machines can fail, and in such cases, the system has to re-execute some of the tasks that were scheduled on those particular tasks. So that was all taken care of by the Hadoop and MapReduce environment. So that was MapReduce and Hadoop. Then came in HDFS and MapReduce. So HDFS, as we discussed, was a distributed file system that comes along with Hadoop. So this was a distributed file system that was deployed across all of the nodes, like distributed nodes, and no matter where your data resides, you have a unified view of the data that you can access the data in the distributed nodes. So, but the main purpose of designing HDFS was to facilitate Hadoop and MapReduce nodes to actually work distributed on their own local storage that was part of HDFS. So this essentially resulted in very high throughput and low latency, and eventually facilitates the MapReduce and parallel processing nodes. Finally, we didn't actually cover yarn in our lecture, but just to give you an overview, yarn is actually a cluster manager. So resource cluster manager. So this can happen like you have let's say 100 node cluster, and so usually what will happen even in a company or wherever you go, you have this a big cluster with Hadoop and MapReduce and Spark already deployed on that. So you won't be the only one using that particular cluster. There will be a lot of other people using as well, and several concurrent applications will be running on those clusters and those frameworks at the same time. So to avoid any clashes and to manage resources, these yarn is yet another resource manager and resource node, I guess, node manager. So this is just a resource manager that manages all of the resources. Several, if there are multiple applications submitted to this particular node or this particular cluster, how to execute them. So this is all handled by Yarn and these resource managers. So that was a basic review of MapReduce and Hadoop. Now moving on to Spark. So first we'll see why do we want to why did Spark came along? What were some basic issues with Hadoop? Uh, how did Spark improve on that? Then we'll go through some of the basics of Spark, and finally I'll show you some of the actual code to do the same word count that we did for Hadoop. So This is kind of a timeline for Hadoop and Spark. So back in 2002, Google like proposed the idea of MapReduce. 2004, the MapReduce paper came out. 2006, Yahoo actually implemented Hadoop based on MapReduce. Then in 2008 summit, Hadoop was, I think, added to the Apache framework. Then back in 2010, Spark paper came out, and but by 2014, Apache's Spark was like added to the Apache framework, and it's one of the top tool of Apache framework and Apache libraries that is currently used by not only in academics but in academia, academics, and all of the like it's kind of all around right now. So, and most of the industry, like right now, most of the, I would say, most of the industry right now has already shifted from Hadoop to Spark. So, this is kind of an architecture of Hadoop and Spark. So Spark is not like there is a hype that says that Spark is a replacement for Hadoop. So there are already, as I told earlier as well, that like most of the industry has already shifted from Hadoop to Spark. But still, there are some basic like use cases that are not suited for Hadoop, not suited for Spark, and MapReduce is like we can't say that MapReduce is like totally dead after Spark. So Spark can actually run on top of Hadoop. So Spark can reuse a lot of resources that Hadoop already uses, like we discussed, like Yarn and HDFS, and it can like at the same time, like it can run on top of Hadoop, and it can also run separately, totally separately from Hadoop. So this is not like Spark is not a total alternative to what we would say Hadoop, but it improves a lot on a lot of other things that previously the only option to do them was Hadoop, but now Spark is a much better option to do that. So as I told you earlier that so this is kind of as I said, the Spark can work on top of Hadoop as well. So the green part here is Hadoop, and the blue part is Spark. So as we can see, the Spark can run on top of this slide gives you an overview of how Spark runs on top of Hadoop, and this is like how Spark run without Hadoop. So Spark can run without Hadoop, with or without Hadoop, or with or without MapReduce as well. So there are several components. I'll talk about that later. And on top of that, are developed on top of Spark as well. But Spark is kind of pretty flexible right now. That it can work with a lot of systems, a lot of whatever it reused. So the main idea of Spark was already like although it presented a total new idea of in-memory processing, but it built on top of a lot of other like um, already available libraries and concepts that it actually reused, and that allowed Spark a lot of people to like freely and adapt to Spark very fast without having to like change a lot of things. So this is another a comparison between Hadoop and Spark. So what actually happened in Hadoop? Hadoop was a what you can say is Hadoop and MapReduce is a general batching framework that was designed. Then there were a lot of like other use cases came in like streaming, how to process streams of data that are real-time streams of data. So generally, like Hadoop was developed for batch processing. So Hadoop was not developed for stream processing. But then later came in the use cases of streams of big data streams. Then there is another use cases of iterative processing. So this is like you maybe you've heard a lot about machine learning and AI. So that involves a lot and lot of like iterative processing. So although like Hadoop can do iterative processing, and there is a framework known as Mahout that was developed on top of MapReduce to actually facilitate machine learning. This was separate from Hadoop, and this was developed on top of Hadoop. Other than like it wasn't a part of core Hadoop. Then, like moving on, there were a few other frameworks like structured. So a lot of people and a lot of developers were mostly familiar with structured languages such as SQL. Um, so what happened is that it was a bit difficult for such developers to from database background to adapt to a totally new architecture. So people came up with like Pig, Hive, Drive, Impala, and all of these frameworks that they were again developed on top of Hadoop. They were not part of core Hadoop. So to these frameworks actually facilitated these structured, they provided these structured languages on top of Hadoop, so that people can familiar with structured languages can work with this. And finally, the graph applications have become like recently much popular. So there were like there are a few libraries like Giraffe. Uh, but all of like the point to note here is that originally MapReduce and Hadoop was developed for batch processing. Then came in a lot of other use cases as well, and several people came up with these extensions to Hadoop that developed on top of Hadoop, MapReduce and Hadoop, but they were not part of the Hadoop ecosystem. So what happened here is that Hadoop was there, but it didn't provide a unified vision or a core to handle all of these cases. But when Spark came in, so Spark came in as a one core library which had like support for most of the above stuff that we talked about. So Spark, there is a Spark core. Then Spark had already had a Spark streaming for interface for real time to process real time data, and it has an MLib machine learning library interfaces for iterative processing, GraphX library for graph processing, and Spark SQL and data frame for structured data. So as you can see, for general Hadoop, so there were a lot of like uh, operational costs, and these would involve because people had to learn a lot of these things. But in Spark, if you learn one thing, you are pretty much like okay with you can work with like most of these libraries by themselves. So Spark by default provided a unified approach as compared as opposed to Hadoop, which had a non-unified like Hadoop. But it wasn't Hadoop like fault because Hadoop was originally developed for batch processing, and later these use cases came in. But this happened to be like Spark had a unified approach for most of these use cases already available. So Spark versus MapReduce the data flow. So let's say a simple Hadoop. So this is a simple Hadoop. We discussed this in our last lecture as well. So this is how a Hadoop job works. So data is read in the system through HDFS. Then we provide like work on some like map reduce operations. And this it is called ETL. So this is kind of extraction, transaction, transformation, and so the extraction transformation logic. So this is just like read data from HDFS, provide apply some logic, and write the results to HDFS. Mahout, as we discussed, is for in a couple of slides before, was developed for machine learning and iterative processing. So again, the data flow was similar. Like you read data from HDFS, you trained your model, and then you write your data to HDFS. However, one thing to note here is that Mahout and these all of machine learning languages involved a lot of iterative processing. So this is not like simply read data from HDFS, train and write, but it involved a lot of such like several multiple of such processes. So read, train, write, read, train, write, read, train, write, read, train, write. So a lot of like this happens multiple times. So this is how the data flow worked in Mahout. And finally, for Hive as well, the data was like Hive is a structured, it provided an SQL like interface to work with on top of Hadoop. So the data flow is again same. You read data from HDFS, query your data, and you write your results to HDFS. So this is Hadoop generally, and Hadoop and all of its like other ecosystems. As compared to that, this is how Spark works. So Spark reads data inside. Spark read data into memory once, read data from HDFS into memory, and now once data is in memory, you can do anything that you want. You can provide like apply ETL operations. You can train, and you can query the same data that's in memory. And finally, once you are done, you can do all of these things without even without writing to HDFS. You can do that while the data is in memory, and once you are done with all of these operations, you just have to write once the final results to the HDFS. So here you can see that we are like saving upon multiple writes, that are multiple reads and multiple writes. In this particular case, these are like two writes and at least two reads that we are saving on. So that's, if you're talking about big data, that's a huge improvement. So that's the basic data flow difference between how Spark and MapReduce and Hadoop works. So just like why this is a huge improvement. So just to give you a perspective, uh, so if you want to read data from CPU to memory, you want to like process your data and you want to move data from CPU to memory, the bandwidth that's provided and throughput is like around 10 gigabits per second that you can do. So that's what Spark does. That what Spark can like utilize. On the other hand, for Hadoop-based system that have to read and write and move data from CPU then to disk, from CPU then to disk, the cost is like, compared this to like 10 gigabits to per second to hard disk is zero point 0.1 gigabits per second. So that's like, in terms of computers, that's like if you do a task in one day in memory, while you are in memory, so consider it like 1 year if you are like more than 1 year if you are on a hard disk. So that's a lot and lot of difference. So that's actually where Spark actually took care of all of this improvements and performance gain that it got. So one may argue that there are faster hard disk available, the SSDs and all of this, but still those SSDs and are not fast enough as memory as we can see. So that's how much difference Spark made while keeping data in memory, excuse me, as compared to Hadoop that has to like go for every job, had to go and write that data in hard disk and read it again for next job. So moving on. So as I told you earlier, that the main like use case, not the main use case, but still one of the major performance improvements of Spark was for iterative processing. That for a processing that in which you have to like process data, the same data again and again and again and again. So this usually happens in machine, as I told you earlier, in machine learning algorithms. So Spark is really fast and for iterative algorithms as compared to MapReduce and Hadoop, because it just reads data once from HDFS and then it can process and iteratively process that data while it is in memory. So a simple example is a k-mean algorithm in this particular slide. So HDFS read, it maps, then group by, then it reduce, and then it has to do an HDFS write. So this is just one iteration that has to be done in MapReduce. However, in Spark, you just read data once. You can like map, group by, network, reduce, and you don't have to like write. You can just go back and map, group by, reduce, map, group by, reduce as much as you want. And once you are done with multiple, like let's say 1,000 iterations, you can finally go ahead and write the results to HDFS. So compare that to Hadoop, that you have to do the same reads and writes more than like 1,000 times. So that's a huge improvement if you are like in case you are working with like big data. So this is like a performance study that um, like shows the time difference for k-means and logistic regression. So both of these are machine learning algorithms, and they involve iterative processing. So as you can see, if Hadoop was doing a particular task in 121 seconds, Spark was able to do that in just 4.1 seconds. Similarly, logistic regression, if Hadoop was doing it in 80 seconds, Spark was able to do it in less than a second. So if you go to like Spark and their documentation, they say that they like especially for these iterative processing, they are able to provide up to 100x performance gain as compared to Hadoop. So this is like a huge improvement. And this is why industry is nowadays moving from Hadoop to Spark for these, especially for these workloads. And another example is like another advantage of using Spark and Hadoop is like if you remember from last time, the word count is similar. The word count here is similar on the left. That shows you have to write a map function, a reduce function, and you have to write some main code as well in order to work with do the map reduce. But on the right hand side, it shows the Spark code. That's just like 3 or 4 lines of code. So it's doing like both of these are doing the same exact thing. So I'll show you the code as well. We'll go through that as well. But this is just to give you a simple comparison that Spark provides not just in terms of performance, but also in terms of development and maintenance. Spark provides a lot of like improvements on top of Hadoop. Again, like it's saying the same thing. Like performance gain from map reduce. These red stages are actually reduced from for Spark jobs. The main improvement for Sparks is from like avoiding the disk I/O and all of the costs associated with the reading and writing again and again to the intermediate jobs. Spark definitely do that using memory-based data processing framework. So what it does, it keeps data in memory as long as you want, and you can do a lot of operations while keeping that particular data in memory. And we also went through some of the how sorry, excuse me, like not in terms of just performance, but also from code and maintenance and development perspective. Spark is much better than Hadoop. So now that we have established that Spark provides like many improvements on top of Hadoop and for a lot of use cases, let's go some of the basics of Spark. So Spark is basically these were some of the basic goals that were listed in Spark while it was developed. It's originally developed in Scala. So Scala is I won't say an improvement to Java, but it can run in the same like JVM that usually Java runs in. So Scala is actually a functional programming language that runs in the same JVM that Java runs, virtual machine that Java runs in. So you don't have to know Scala to actually work with Spark because Spark provides APIs in Scala, Java, and Python. So all three are possible. So you don't have to worry about like if you don't know Scala, you can't work with Spark. You can always work with Spark. So that's not an issue. Yes, so to work with Spark, there are two ways. The first one is Spark Shell, and the second one is writing similar to application. So the applications are similar to what we did for Hadoop. So if you remember, you wrote some application, you compiled it into a jar, or you wrote some Java code, then you compile it, created a jar, and then you run that jar in Spark. So that's usually how things that the application developed and how things are worked. For Python, you wrote some code already, and once you have that code script, you submit that via Hadoop streaming. Uh, and then using that particular code on the data that you specified, the Hadoop framework was able to like run that particular application that you wrote. So this is similar to how like for the Spark application, it's kind of similar. You write your code in Java, Spark, or Scala, Java, Python, or Scala, and then you submit it to Spark. However, there is another interface that Spark provides, that's Spark Shell. So it's kind of an interactive that you just open up a terminal, you write your code, you can you write your code as you are going along. So it provides a more interactive feeling, but it's not in Java. It's either available in Python or Scala. So it's more like for data science people, like not for just data science people, but that's how I've seen most of the data science people make use of Spark Shell. You can always do that, and it provides. Uh, I'll show you both of these types later in this lecture. So this is just some example of Spark Shell. You just run it. It provides you the left side is the Python Spark Shell, and the right one is the Scala Spark Shell. Now we don't need to go through this. Yes. So like you have to keep these four terms and in mind, like always. Whenever you are working with Spark, these are the four basic fundamental properties of Spark. So the first one is Spark context. So I'll go through this like again and again and again and again, because these are the most fundamental and basic like abstractions of Spark that like you have to understand if you want to work with Spark. So the first one is Spark context. The second one is an RDD, known as resilient distributed data set. The third one is transformation, and finally the actions. So just keep this in mind. Like if you want to work with Spark, um, like um, apart from like what is the advantage of Spark, if I want you to keep with you something to keep with you, these are if you want to keep Spark in memory, these are the four things that you have to understand. These are the four musts that you know what these are in order to work the Spark. So Spark context, RDD, transformations, and actions. So I'll explain this one by one. So again, Spark context, RDDs, transformation, and action. Again, like saying it like I cannot emphasize the importance of these four as much as I can, but I have to keep repeating this: Spark context, RDDs, transformations, and actions. So let's say let's go through one by one. What is a Spark context? So every Spark application has to have a context. So I'll explain what a Spark context is, but it's kind of, if you are from coding perspective, it's kind of the main entry point or the main function from where your Spark application starts. So whenever you are working with Spark, you have to create a Spark application. You have to have a Spark context. So remember, there are two ways to work with Spark: Spark Shell and Spark application. So if you are working with applications, you have to create a context. So I'll show you how to create a context. But if you are working with shells, the shell already has a Spark context, and you can that is the variable known as sc. So sc dot anything is sc is the Spark context for all of the Spark shells. So this is showing how Spark context work with cluster managers like Yarn and all of this. So there's a standalone application. You write your driver code and you submit that through Spark context. So Spark context, like you are like wherever you are submitting the application, is the Spark context. So it's kind of you have a cluster running and you have to connect that to that particular cluster. You will do that through Spark context. So you either connect to the cluster via Spark context, so you can directly connect, or you can connect to a resource manager, or like anything that you have to do with the cluster is through Spark context. So again, the same thing, there is a Spark. So you write your program, you are working as a Spark client. So in the Spark client you create a Spark context. So whenever in your code you create a Spark context, it creates a Spark client. That client connects to a Spark cluster and then manages all of the workers and runs your applications. So Spark context, whenever you want to work with, the first thing is Spark context. So you created so on the left is the first line is like val sc is equal to new Spark context, blah blah blah, whatever the like arguments are, but the first line is creating a Spark context. Now let's move on to the second concept, that's the resilient distributed data set, or in other word I'll say that like RDD. So this is not abstraction of, like, this is the main abstraction and the main contribution of the Spark and the Spark community. So instead of keeping data in on disk and reading it every time, the basic data structure that Spark people provided was an abstraction of in-memory data. So resilient distributed data set, what it provided was, let me show you. No, we don't have that. So it's kind of like you read data from HDFS, and that data is distributed across all of the nodes. So just think of it as like although your data, like partitions of data is available on memories across nodes, but you can access this RDD from the master as like a single pointer. So an RDD is a pointer to your in-memory data across nodes. So just to understand. So just like the resilient distributed data, so the resilient is if data is in memory. So if you know that memory is a volatile. So if you shut down your computer, your data is lost. However, this is known as they call it resilient because the way they structured, or the way they perform the structure this data is that if data is lost, it can always be recreated. The second is distributed, as we it is your data is partitioned across the nodes of the memory, and finally is a data set a resilient distributed data sets. That's how it is termed, and the beauty here is that the data structure had the data structure name has all of the important factors of this particular abstraction. So RDDs provide whenever you create an RDD, so you have Spark context. Using Spark context, you create RDD. Just like keep that in mind. Spark context using all Spark application have to have a Spark context. Using that Spark context, you create an RDD. So once you have an RDD, RDD is data in memory. You can apply, you can write your own logic to process that particular data that is in an RDD available in distributed nodes across the memory. So there are two types of applications that there are two types of logic that can be applied on RDDs. So they are terms of transformation and action. So those are the next two things that we'll talk about. Just to keep in mind that an RDD is just a list of partitions of data that are available across all of the nodes. So these are like details of RTD. I don't want to go into a detail, but if you're interested, you can like always like read about them. So in this particular, since this is an intro, I don't want to go into like a very detail of that. It's a immutability and lineage and fault tolerance. So these are like kind of a somewhat advanced concepts. But just to keep in mind, Spark context, again saying every Spark application or Spark shell has to have a Spark context. You create like once you have a Spark context, you can create an RDD using that particular Spark context. How to create an RDD? So that is an important question. Like using so there are several ways to do like create RDDs, but remember, using the Spark context, you create an RDD. So an RDD can be created from a file on HDFS or on any distributed like HDF on any file storage. So that file storage can be local. So it can be local. It can be on distributed like HDFS or Google file system or like any file storage. But there are some limitations to local. Uh, local file system, but there are always ways to do that. But in general, what I would say is that the first way to create an RDD is from a set of files. So that files can be on local, that can be on HDFS, that can be on database, or that can be on a NoSQL database or SQL database, blah blah blah, like whatever. But just to keep in mind, the one way is to create an RDD is from files. Okay. The second one is from data that is already in memory. So and finally from another RDD. So there are like transformations, there are RDDs that can happen. Like you have one RDD, you want to create like another RDD from combining two RDDs. So yes, and then there are some ways to create RDDs from sockets, and so yeah. So there are a lot of ways to actually create RDDs. So some of them are like files, data in memory from another RDD from socket. Um, yeah, but for our purpose, just like keep in mind that using a Spark context, we create an RDD either from file, socket, or another RDD. So this is just to give you an example of how to create a file-based RDD. So as like SC, here is the Spark context. So using the Spark context dot text file, you read in a purple cow dot text dot txt file. So that's the file that you want to create. The file here is it contains I've never seen a purple cow. I never hope to see one, but I can tell you anyhow. I'd rather see than be one. Okay, so this is the content of the file. So once you do sc.text file and you give the path of this like purplecow.txt, the RTD created will have like each the RTD will create a list of like each line present in the file. So that's how an RTD is created. But just to keep in mind, I'll show you this again, that an RDD although will be created, but it won't be materialized until like macdata.count is called. Why is this happening? I'll explain that later, but just to keep in mind, this is how an RDD is created from a file. So you like sc.text file, and you give it the path of the file. For each line in that particular file, it create an art. So what it does is actually read each line, like create partitions of this file. Let's say 1, 2, 3, 4. There are four lines in this particular file. So what will happen is that Spark context or Spark will divide this file, let's say, into four lines, and if across let's say we have two Spark workers, so two lines will be read on one node and other two will be on the other node. However, if you want to see this RDD, this whole RDD as a whole across nodes will contain all of the data that was there in your file. So now we are done with the first two parts, Spark context and creating an RDD. So using Spark context, we created an RDD. So what to do with RDD? So there are two set of functions. The first ones are transformations, and the final one are the actions. So how are these two different? Just like before going into the details, so transformations are not materialized, or transformation are just like kind of an intermediate functions, but they are not applied to the RDD unless there is an action. This is important. So this is an interview question for Spark. So what they will do is they can give you a set of commands, but they'll all be transformations, and they'll ask you, okay, so what will happen if you run this code? So although all of the logic will be there in the transformations, but there won't be any action. If there is no action, nothing will happen in that particular Spark programmer's Spark script. So Spark codes or Spark scripts or Spark, nothing happens on an RDD unless an action is performed on that particular RDD. So this is an important statement to keep in mind. So yes, again said, two types of operations. Transformation define a new RDD based on current RDDs, and actions actually return values. So RDD transformation is just a set of transformation on an RDD that define how they should be how these RDDs should be transformed. So transformation is lazily evaluated, as I said, like they are not performed until there is an action. So this is important. Like this actually helps in a lot in actually optimizing Spark code in the backend. But just keep in mind, like I don't want to go into details of that. But these are just to keep in mind, they are not processed until there is an action. So some examples of transformations are like map, filter, group by key, sort by key, etc., etc. So map in our case is if we have sc.txt file, we created like an RDD. RDD is equal to sc.txt file, and then we do rdd.map, and then we exit our application. So nothing would happen. So no map will run actually unless we provide an action after that. So I'll explain that later. So let's go through the example of the same purple cow file. So the first line, what does that? The first map does, it reads in each of the line, it converts that all of the letters to uppercase letters. So what will happen is that, okay, I have never seen a purple cow, I have never seen a purple cow, blah blah blah. So all of the after first map, what will happen is that all of the content will be in uppercase, and then you filter every line that starts with an I. You filter you just keep those lines, and you discard rest of the lines. So now what will happen? You just have three lines. So this is how transformation works. But again, finally, the actions. So the actions, like none of this previous would work unless there is an action after this. So some of the examples are like count, take, collect, save as text file. So these are all of the some of the actions that have to be performed in order for all of these transactions to work. So yeah, this is a good example. So this is your again your purple cow.txt file. Data is RDD is not processed until an action is performed. So this is again very important. So let's go forward. The first step, you created an RDD. So my data here is an RDD is equal to sc like spark context dot text file, and then you give it the path of path of the file that is on the distributed system. Let's say HDFS. So you created an RDD, but as you see on the right, my data right now is empty. It does not have anything. So although you created an RDD, there is nothing in there. So the first map that you performed is like you converted all of these, like all of the lines in this particular RDD to uppercase letters. So again, you see here like my data underscore UC like uppercase is another RDD that is like created after applying a map function to the original RDD that was my data. So, but again, note here is that my data underscore uppercase UC again does not have anything in it. It's still empty. Nothing is there. Nothing happens right now. So again, finally, you apply another transformation that is filter. So as we did like earlier in last slide as well. So we filter all of the lines containing data with that containing lines starting with I. So that was just three lines. But again, see on the right that there is nothing in the RDD. So finally, we have a third RDD that is my data underscore filter. So we created this like now there are three RDDs: my data underscore UC, and my data underscore filt. However, no data is there. Like although these like RDDs are supposed to be created in memory, but right now they don't have any data since there is no action. If you find like my data underscore filt dot count, so remember count is an action. So all of the processing, all of the materialization will happen only once an action is encountered. So now you see as soon as an action is performed, now all of these like intermediate RDDs will like go ahead and be materialized, and then these transformation will be applied on that, and finally we'll get a result that is like okay, we have three lines that were starting with I. So yes, these are like the basic, all of the basic concepts. Again, the three, like the four basic concepts of Spark. You create like a Spark. You always work like all Spark application and all Spark code has to start with a Spark context. That's the first thing. Using Spark context, you create an RDD. So an RDD is an abstraction for data in memory. There are two types of operation that can be performed on a particular RDD, and these operations are either transformations or actions. The difference between transformations and action is that like no matter how many transformations are there, they won't be processed until an action is performed. So if so, these are the again the final four things: Spark context, RDD, transformations, and actions. So if you want to work with Spark, these are the four things, and that's these are the four things that you'll work with. Yeah, so I won't go into the next details, so that's all for this lecture. Now, just briefly, I'll show you the code to run the same word count code that we did for Hadoop as well. Thank you.